Hello there, ATS EVS 105 students, Dr. John Schragi, and I'm just continuing today our lecture series that's about the scientific method, which is sort of one of the big themes of the course, is how we use the scientific method to build the modern world. And the part we're on today is part 2, which is about constructing hypotheses. You know, when scientists are doing science, we're not just playing. I mean, sometimes on TV it makes it sound like, you know, when they show scientists in the movies or something like that, like we're just sort of guessing or trying things or whatever, and, you know, just sort of saying, look at this, the mean pH of the water is whatever. No, we're not just playing and trying things. I mean, just sort of measuring and trying and getting ideas isn't really exactly part of the scientific method. I mean, it is part of being intellectually curious about the world and kind of finding things intellectually stimulating. It can be part of the formulation of a research question, which we learned way back in, I think it was the first module of this course. But now we're working our way further through the scientific method about how we're going to use this process of creating experiments and working with data and so on to actually have knowledge about the world. And the one that we're doing right now is about step 2, which is about formally constructing a hypothesis. Now, as you guys know, I have 2 little boys. And my 2 little boys love Thomas the Train, and they love all kinds of things, but one of the very, very favorite things is a show called Dinosaur Train. You guys are probably a little too old. You probably never saw Dinosaur Train. It's a PBS cartoon show about science, and these dinosaurs are on a time-traveling train, and they travel around into different eras, and they get to meet all kinds of dinosaurs. And Buddy the dinosaur, who's sort of the star of the show, he always has a hypothesis. That's kind of the catchphrase of the show. I have a hypothesis. And Buddy will have a hypothesis that the dinosaurs they just met use their feathers to fly. And then they can test the hypothesis where they say, so Mr. Velociraptor, can you fly? And Mr. Velociraptor tries and he can't. Okay, I guess my hypothesis was wrong. Or I hypothesize that this brachiosaur has long legs so that she can eat off the branches at the top of the tree. And then the brachiosaur tries it, and sure enough, they can get the branches off the top of the tree. And if you're like of the toddler set, this is brilliant. I mean, it's dinosaurs and trains. Doesn't get much better than that. So what the kids are learning here is about constructing logical ways to develop information. They're learning about hypotheses. You know, on the Dinosaur Train, practically every time Buddy says, I have a hypothesis, somebody says, what's a hypothesis? And then some wise, you know, Velociraptor or Troodon or something says, oh, a hypothesis is an idea that can be tested. I think we need a more scientific definition than the toddlers get. I mean, I like this, knowing the answer already, I know that I like this first definition here about it's a supposition or proposed explanation made on the basis of limited evidence that can be a starting point for further investigation. That's a really good definition. Although from philosophy they have a second definition that is a proposition that is made as a basic for reasoning without any assumption that it's the truth. I like that too. Both of those are going to be part of our idea. Buddy the dinosaur starts with some limited information. Gee, he's seen other dinosaurs that use their feathers to fly. And then he makes the generalization that, well, that other theropod dinosaur will also be using his feathers to fly, and then they find out whether it does or it doesn't. He's not assuming it's true that the dinosaur is using those feathers to fly. He's saying let's use that as the beginning of where we're going to be examining the truth. Well, in the formal scientific method, how, like, you know, science gets done, we are going to be constructing experiments. They're going to need actually 2 hypotheses. And these hypotheses have names. One is called the null hypothesis, and the null hypothesis has the symbol H0. And then the alternative hypothesis, which has the symbol HA. And you're going to do an experiment, and when you do experiments, you construct 2 hypotheses, 2 ideas that can be tested. That you're not necessarily making any assumption as to which one's true, but here's the deal. If I take these 2 hypotheses here, you know what? It's easier to think about it if we have a concrete example. How about we make a concrete example from like a medical community? H0, one hypothesis could be, this cancer treatment has no effect. We can do it all we want, we can give this chemotherapy or whatever to this person, and it makes no difference to anybody. HA, the alternative hypothesis, could be, this cancer treatment has an effect. Alright? These are our two hypotheses. We're not presuming anything about which one's right. They're just a starting point to try to figure out and have actual knowledge. It's very intrinsically valuable to have knowledge about which of these two is correct. Does my cancer treatment have an effect or does it not? Now, when you construct a pair of hypotheses, though, like this, they have to have very specific properties. In particular, they must be what we call exhaustive. Now, this word exhaustive is a little bit hard. You don't necessarily use it in your day-to-day life. Exhaustive means that it includes all possibilities. There is no possible outcome that isn't described by one of these things. In this case, then, our two hypotheses are exhaustive. Either the treatment has an effect or the treatment does not have an effect. There is no third possibility. The hypotheses need to be exhaustive. Every possible outcome that could be the truth has to be described by one of those two hypotheses. Another property that our pair of hypotheses must have is that they must be mutually exclusive. Now, mutually exclusive is another term that people tend to use kind of casually in conversation, but so that we have a dictionary definition here. Mutually exclusive is a statistical term that is used to describe a situation in which two events do not share an outcome. They cannot be occurring at the same time. So I have two hypotheses. One, the cancer treatment has no effect. Two, the cancer treatment has an effect. Well, they are exhaustive. They include all the possibilities. On the other hand, they're also mutually exclusive. If the first hypothesis is true, the second one must be false. If the second one is true, the first one must be false. Now, this is brilliant. This is a really useful thing. Like I said, I have this example here. I now have narrowed it down. There are two possible outcomes that are exactly one of which is true. There's no way they're both false, and there's no way they're both true. If I can then figure out which of these is true, I have gained real knowledge about the world. And I don't actually have to figure out which one is true, I just need to figure out which one is false. And that is a very, very interesting bit of insight here into the logical way that we've constructed these hypotheses. All I have to be able to do is take a look at one of them. Let's take H naught. In fact, in practice, that's the one you're going to be looking at. And you say, if I can prove that one is false, or at least show that that one doesn't seem to be consistent with observations, or doesn't seem to be consistent with models, or whatever, well, I can say if H naught is false, HA must be true. Oh, this is really powerful. This says that if we can look at the data and say H naught is very unlikely, all right, so if I take my example here of cancer, when I give chemotherapy to people, this treatment here, you know what? Some of those people are going to get better. Some of those people are not going to get better. Okay, but some of those people might have gotten better anyway. Their immune system beat the cancer back or something like that. Or usually people are on more than one treatment at the same time and all that kind of stuff. But if almost everybody's getting better, that's interesting. And if maybe I have two groups and one group has not received the treatment and another group did, and the people who didn't receive the treatment are not getting better as much as the people who do, that's all evidence that maybe the treatment is working. More importantly, it's evidence that the H naught is false. The treatment clearly does have some effect. Now later, in a later lecture, in the next module I believe, we're actually going to show how this is all quantified. We don't just sort of say, it doesn't appear that H naught is true. In the same way that Buddy just sort of asks a velociraptor if he can fly. Okay, on the other hand, there will be quantitative tests that we do on our experimental data or our model output or whatever to tell us, can we reject the null hypothesis. And that's actually jargon there. Reject the null hypothesis, accept the alternative hypothesis. If the data is not consistent, if the data are not consistent with H naught, then we have to reject H naught. Well, if H naught is false, then HA is true. And so we accept the alternative hypothesis. If it turns out the data aren't all that inconsistent with H naught, in this case, if most of my patients are not getting better when I give them that treatment, or not getting better at any higher rate than when I didn't give them the treatment or something like that, then we cannot reject H naught. I'm not necessarily saying that H naught is true, but I can't say that it's false either. And so our experiment kind of has no result. So see, when we construct these two hypotheses, when I first told you, hey, I'm making two hypotheses, one is the cancer treatment has no effect, one is that it doesn't, I didn't tell you which one was which. But actually, H naught has to be the one about the cancer treatment has no effect. That has to be the kind of, the police line there. It's the move along citizen, there's nothing to see here outcome. If my cancer treatment that I'm spending $1 billion developing doesn't do anything, okay, move along, we gotta do something else. If any kind of experiment, this group is trying to lose weight, okay? H naught, this new technique of losing weight doesn't work. HA, this technique of losing weight does work. Okay, they're mutually exclusive, they are exhaustive, and the null hypothesis is that there's nothing to see here. It doesn't work. Okay, so you have to construct your hypothesis testing that way. Well, let's actually take a look at this in the context of climate change. I mean, I could make a pair of hypotheses. Let's say my null hypothesis, H naught, is that the temperature of the planet is not changing. And then the HA is the temperature of the planet is changing. Okay, they're exhaustive. Either the planet's temperature is changing or it is not. Alright, they are mutually exclusive. Only one of those two things can be true. They cannot both be true. So they can't both be false and they can't both be true. Alright? And frankly, this sounds like the kind of question our society needs an answer to. What we do is we start off, what if H naught is true? Alright, let's assume that it's true and then we go look at the data. I'm trying to say, is it true that the planet's temperature isn't changing? Alright, we can go and maybe get observations, all the kind of stuff we did in like modules 1 and 2, where we were looking at temperature change data from stations and from sea ice and from glaciers and oceans and things like that, and we can say, I mean, it doesn't really seem to be the case that that is true. Now again, in real life, as we'll see in the next time that we do a lecture about the scientific method, this is all quantitative. There's actually a quantitative way you test this, where you say, how do I know that the temperatures are changing enough that there's no way H naught is true? Because if H naught, if it's not consistent with what we see in the data or in the models or whatever, then we reject H naught. H naught can't be right. Okay? Or maybe that does show, that's not what it shows. Maybe the temperature data doesn't show that the temperature is warming. In that case, hey, H naught sounds fine, and we keep it, we accept it. Okay? But in our scientific method, if we're saying, hey, the data are showing that the temperatures seem to be getting warmer, it's awfully unlikely the planet isn't getting warmer, yet somehow or other, I suppose it's possible that all these weather stations are wrong, right? Like they're all got calibration problems or something. Or maybe we weren't measuring out all these glaciers right or something like that. It's not that that's impossible, but gosh, it's getting less and less likely the more and more evidence we have. Then we reject H naught. Our victim hypothesis, our null hypothesis. Victim hypothesis is sometimes what stats majors call such a thing. Because you're like trying to sacrifice that one. And, well, if H naught is wrong, then the more interesting HA is true. So we have to accept, again, that's the jargon, is we accept HA, alright? We have accepted our alternative hypothesis that in this case the planet is warming. We'll learn more in future lectures about how actually we'll decide whether we can accept HA or we have to reject HA and all, H naught, if we have to accept it or if we can reject it and all that kind of stuff in general and also in the context of climate. But here's the deal, I don't want to understate this here. Hypothesis testing built your modern world, okay? Every medical treatment, every way that we increase the production of food on our planet, every way that we improve our ability to make cars safer, everything that we do to develop ways to make energy, everything the modern world does is about hypothesis testing. We have medicines and technology and so on because of the scientific method, and in particular this idea of developing hypotheses. It is in fact one of the greatest inventions in the history of humanity, is our ability to use logical ways to develop a pair of hypotheses in such a way that when we test them, we have real knowledge about the nature of the world around us. That is important. This gets us through the second step of the scientific method as the way we're breaking it up. In future modules, we'll be talking about how you actually quantifiably test your hypothesis, and then finally about how you can publish those results so that that information is shared with the scientific community. Alright, that's all I had for you on this fairly short lecture. Please let me know if you have any questions. This has been Dr. John Schrage.